Question 4.1 is interested in us calculating the magnitudes of velocity and acceleration at this point A. And this is a disk that's in a fixed axis rotation about this point here. So I'll just make a quick sketch of that. Okay, there's the fixed axis in the middle, and it wants us to find out what the velocity and the magnitude of velocity and the magnitude of acceleration. And this is linear velocity and linear acceleration, as opposed to angular velocity and angular acceleration, which are given as part of the question. It says the disk's angular velocity is 2 radians per second, and that from the diagram is in this direction, 2. And you've got an acceleration, an angular acceleration, which is in the same direction, which is 6 radians per second squared. Now our symbol that we use for angular velocity is omega, so omega is 2, and the symbol we use for angular acceleration is alpha, and that means alpha is equal to 6 radians per second squared. So let's start with velocity. Now velocity is the simpler of the two. If we look at our notes from the end of lecture 4, you've only got one, in fixed axis rotation, you've only got one component of velocity, and this is the tangential component. And the tangential component has a simple expression, which is just r times omega. So that's there, look. And this r here is given in the question as 0.2 meters. So that means this is equal to 0.2 times 2, which is equal to, just make sure I don't make a stupid mistake, 0.4 meters per second. So that's because there's only one component, the magnitude of that, which is what the question asks, so the mod of the the tangential component is just 0.4. So that's the first part of the question, just 0.4 meters per second. Now the acceleration is different because if you go back to the lecture slide, to the summary lecture slide, you've got two components, a centripetal component, A sub r, and a tangential component, which is A sub t, and these have these magnitudes. So let's start with the centripetal component, which is AR, and then we'll in a minute do the tangential component. Okay, so AR, which is towards the fixed axis, has, from our notes, we know magnitude is r omega squared. It's got to be squared because obviously the direction of rotation doesn't make a difference to the direction of the centripetal acceleration. That's always to the centre. So that's r is 0.2 again, times omega squared. Omega is 2, so that's 2 squared. That's going to be 0.2 times 4 is equal to 0.8 meters per second squared. The tangential component, so this is this component here, that has a magnitude of r alpha, where alpha is up here, is our angular acceleration. So r alpha is 0.2, again r times 6. 0.2 times 6 is 1.2 meters per second squared. So those are the two components. To get the magnitude, we take the mod of the acceleration, the total vector. So these have got two components and they're perpendicular to each other, so we can use Pythagoras to work out what the magnitude is. So that's AR squared plus AT squared. So what we're doing here is that's the total acceleration vector, which is combined of these two components. I haven't drawn that particularly well. And the length of this vector we can work out from Pythagoras. So that's AR squared, so that's 0.8 squared plus 1.2 squared. And if I do that, find the square root of 0.8 squared plus 1.2 squared, we get an answer of 1.44 meters per second squared. Okay, that's that one.